Very good morning, friends. Welcome back to the class. Class AB power amplifier. We have seen that Class A amplifiers conduct 100% of the time, whereas Class B amplifiers 50% of the time, and Class C power amplifiers as somewhere between 0 and 50% of the time. The Class AB amplifier, as its name suggests, conducts somewhere between 50% and 100% of a cycle, depending on the bias levels chosen. As a result, its efficiency and linearity are intermediate between those of a Class A and a Class B amplifiers. These compromise it's frequently satisfactory as one may infer from the popularity of these power amplifiers. We do not need to undertake a separate derivation of equations for amplifier because the equations for the class C case also apply here. They also include the class A and B Class B case. The only difference is that the bias current is positive rather than negative. The power amplifiers presented so far use the active device as a controlled current source. Another approach is to use the device as a switch. The reasoning being that a switch ideally dissipates no power. For there is either zero voltage across it or zero current through it. Okay. Next, since the switch's VI products is therefore always zero, the transistor dissipates no power and the efficiency must be 100%. Okay. The class D amplifier circuit is shown below. The V drive transformer 1, transformer 2, M2, M1, VDD, L, C, or L, or the components are represented in the class D power amplifiers. Next, see figure, it looks the same as a push-pull transformer coupled version of a Class B amplifier. In contrast with the parallel tanks, we typically see a series RLC network is used in the output of this amplifier. Since switch mode amplifiers are the duals of the current mode amplifiers. As a consequence, the output filters are also duals of each other. The input connection guarantees that only one transistor is driven on at a given time, with one transistor handling the positive half cycles and the other negative half cycles, just as in a push-pull class B. Because of the switching action, each primary terminal of the output transformer T2 is alternately driven to ground, yielding a square wave voltage across the primary winding. When one drain goes to 0 volts, transformer action forces the other drain to a voltage of 2 VDD. The output filter allows only the fundamental component of the square wave to flow into the load. Since only fundamental currents flow in the secondary current circuit, the primary current is sinusoidal as well. Class D power amplifiers. As a consequence, each switch sees a sinusoid for the half cycle that it is on, and the transformer current and voltage therefore appears as in figures. So here also given the class D power amplifier circuit and also the voltage and current for ideal class D amplifiers. Next, as a consequence, each switch sees a sinusoid for the half cycle that it is on, and the transformer current and voltage therefore appears as in figures below. Figures below. Figure M1 drain voltage and current for ideal class D amplifiers. T2 secondary voltage and current for ideal class D amplifiers. T2 secondary voltage and current for ideal class D amplifier. Because the transistor acts like switches, the theoretical efficiency of the class D amplifier is 100%. The normalized power handling of this amplifier happens to be P naught by VDS or dot ID dot PK is equal to 1 by pi 0.32, which is better than a class B push pull and much better than a class A amplifier. The class D amplifier cannot normally provide linear modulation, but it does provide potentially high efficiency and does not stress the devices very much. One practical problem with this power amplifier is that there is a no such thing as a perfect switch. So next, class C power amplifier using transistors as switches has the potential for providing greatly improved efficiency. But it's not always trivial to realize that potential in practice, but due to imperfections in real switches, the associated dissipation degrades efficiency. To prevent gross losses, the switches must be quite fast relative to the frequency of operation. At high carrier frequencies, it becomes increasingly difficult to satisfy this requirement. If there were a way to modify the circuit to force a zero switch voltage for a non-zero interval of time about the instant of switching, the dissipation would decreases. The Class C amplifier uses a high order reactive network that provides enough degrees of freedom to shape the switch voltage to have both zero value and zero slope at switch turn on, thus reducing switch losses. The BFL simply provides a DC path to the supply and approximates an open circuit at RF. The capacitor C1 is conveniently positioned for any device. Output capacitance can be observed into it. Here also the theoretical efficiency for E amplifier is also 100%. Waveforms are shown below. Waveforms also given here. Next, the design equations are as follows that L is equal to QR by omega and here C1 is equal to 1 by omega or pi square by 4 plus 1 into pi by 2 is approximately equal to 1 by omega into R dot 5 dot 447. C2 is approximately equal to C1 into 5.447 by q 1 plus 1.42 by q minus 2.08. For maximum efficiency, one desires the maximum q consistent with the desired bandwidth. The peak drain voltage is approximately 3.6 VDD while the peak drain current is roughly 1.7 VDD by R. This is from waveforms. The maximum output power delivered to the load is P naught is equal to 2 by 1 plus pi square by 4 into V square DDD. V square DD by R is approximately equal to 0.577 into V square dd by R. The normalized power output capability is therefore given here, approximately equal to 0.098. Because of the poor power capability and the reduced efficiency due to switch turn-off losses, practical implementations of the Class C amplifier do not exhibit significantly superior efficiency to well-executed designs of other types, that is Class F amplifiers. Class F amplifiers. So here VDD, BFL, BFC, Z0 tuned to omega naught V out, all these components are presented in the class F amplifiers. Class F amplifiers. Implicit in the design of Class C amplifiers concept of exploiting the properties of reactive terminations to shape the switch voltage and current waveforms to advantage. Perhaps the most elegant expression of this concept is found in the class F amplifier. The output tank is turned to resonance at the carrier frequency and is assumed to have a high enough Q to act as a short circuit at all frequencies outside of the desired bandwidth. The length of the transmission line is chosen to be precisely as quarter wavelength at the carrier frequency. Next one, a quarter wavelength piece of line has an impedance reciprocation property, that is the input impedance of such a line is proportional to the reciprocal of the termination impedance. From transmission line theory, Z0 is equal to square root of Zin into ZL. So Zin is equal to Z0 square by ZL. At the carrier frequency, the drain sees a pure resistance of RL is equal to Z0. Since the tank is an open circuit there and the transmission line is therefore terminated in its characteristic impedance. Hence, the drain current is a sinusoidal when the transistor is on. The tank guarantees that the output voltage is a sinusoid even through the transistor is on for only a half cycle. The total peak to peak drain voltage is seen to be twice the supply voltage. Therefore, the peak to peak voltage of the fundamental component of VDS is given as 4 by pi into 2 VDD. Note that the fundamental has a peak to peak value that actually exceeds the total VDS swing thanks to the magic of Fourier transforms. And class F amplifier. Drain voltage and current for ideal class F amplifier is shown like this. The waveforms will be obtained like this. Now, since only the fundamental component survives to drive the load, the output power delivered is P 0 is equal to 4 by pi of VDD whole square by 2R. Since the switch dissipates no power, we can conclude that the class of amplifier is capable of 100% efficiency in principle. In practice, one can obtain efficiency superior to that of class C amplifiers. Next, the class F power amplifier has substantially better normalized power handling capability since the maximum voltage is just twice the supply while the peak drain current is given by IDE of Pk is equal to 8 by 5 into VDD by R. The normalized power handling capability is therefore is equal to 1 by 2 pi, that is approximately equal to 0.16 or exactly half that of the class D amplifiers. Difference between class A, B, C and AB power amplifiers.